Now we determine the internal energy of a von der Waals gas in a given thermodynamic state, which is equal to the internal energy of real gases under the conditions where the von der Waals approximation describes the real gas behavior accurately. When we calculated the specific internal energy U of an ideal gas of mass m at the temperature T, that is the ratio of its internal energy U to its mass m, then we found that it is equal to the specific heat capacity CV of the gas at constant volume, times the absolute temperature T. This formula shows that the only state variable which the internal energy of an ideal gas depends on is its temperature. We also established that the internal energy U of a given amount of substance is a function of its entropy S and temperature T for a fixed number of the particles N of the substance. The partial derivative of the internal energy with respect to the volume at a constant temperature for such a functional dependence contains the partial derivatives of U with respect to S and T. We could replace the partial derivatives of U with respect to S and T by applying some of the Maxwell relations and express the partial derivative of the internal energy U with respect to the volume V at a constant temperature T as minus the pressure P of the substance, plus its temperature T times the partial derivative of the pressure P with respect to the temperature T at a constant volume V. The right-hand side of this equation can be written as T squared times the partial derivative of P over T with respect to T at a constant V. If the substance is a von der Waals gas, then its pressure is given by the gas constant R times the temperature T over the difference between the molar volume Vm of the gas and its volume correction constant V, minus its pressure correction constant A over Vm squared. We can substitute this expression into the partial derivative which gives A over the product of Vm squared and T squared. We express this ratio in terms of the volume V by writing it as the square of the amount of species N times A over the product of V squared and T squared. Here the amount of species N is equal to the mass m of the substance over its molar mass m sub m. If we substitute this result into the partial derivative of the internal energy U with respect to the volume V at a constant temperature T, then we obtain N squared times A over V squared. The number of particles N which is fixed, can be written as the product of the amount of species N and the Avogadro's number Na, that is the number of particles N of a gas is given by the ratio of the Avogadro's number Na to the molar mass m sub m of the gas, times its mass m. Now the internal energy U of a von der Waals gas can be written as the integral of the partial derivative of the internal energy with respect to the volume at a constant temperature, where we integrate along any isothermal path between an arbitrary initial state A with the volume VA and the actual state with the volume V. The internal energy depending on the temperature T, the volume V, and the number of particles N of the gas is the sum of two terms. The initial internal energy UA of the gas in the state A, and the integral of the partial derivative of U with respect to V at constant T, where the integral is performed with respect to V from VA to the actual value of V. Because the initial state A is an arbitrary thermodynamic state, we can choose the volume VA of the system such that it tends to infinity. As a result, the average distance between a finite number of particles or molecules of the substance becomes so great that the intermolecular forces can be neglected between the molecules and the gas behaves like an ideal gas. This means that the internal energy of the system in the initial state A tends to the internal energy of the same amount of ideal gas at the same temperature. Then the internal energy of a von der Waals gas is equal to the internal energy of the same amount of ideal gas at the same temperature, plus the integral of N squared times A over V squared with respect to V from infinity to V. By substituting the expression obtained for the internal energy of the ideal gas into the first term in the right-hand side, we can write it as the mass m of the gas times its specific heat capacity CV at constant volume times its temperature T. The integral in the second term gives minus N squared times A over V. If we insert the specific volume V defined by the ratio of the volume V to the mass m into the second term and pull out the mass m from both of the terms, then we can write the right-hand side of the equation as m times the difference between CV times T and N squared times A over m squared times the specific volume V. Because the amount of species N is given by the ratio of the mass m to the molar mass m sub m, the second term in the parentheses is equal to 1 over the square of m sub m, times A over V. We can absorb the factor 1 over m sub m squared into the pressure correction constant A by defining the constant A prime, and write the specific internal energy U of a von der Waals gas as the specific heat capacity CV of the gas at constant volume times its absolute temperature T, minus the constant A prime over the specific volume V of the gas. This expression shows that the internal energy of a von der Waals gas or a real gas depends both on the temperature and the volume of the gas. We also note that if the volume of the von der Waals gas tends to infinity, then the second term vanishes and the internal energy of the gas reduces to the internal energy of an ideal gas which does not depend on volume. As we can see, the internal energy of a fond der Waals gas is given by the sum of the internal energy of an ideal gas depending on the temperature of the gas, and a second term depending on the volume of the gas. Because the second term contains the pressure correction constant of the real gas, it is not difficult to show that this term is related to the pressure correction term in the fond der Waals approximation given by the amount of species n of the gas times its pressure correction constant A over the square of its volume V. We can see the role of this term in the internal energy of the gas, if we substitute the product of the mass m of the gas and its specific volume V into the volume V of the gas. Then the pressure correction can be written as 1 over the square of the molar mass m sub m of the gas, times the constant A over the square of the specific volume V, or A prime over V squared. The specific pressure volume work done against the intermolecular attractive forces by the gas expanding from its minimum volume, that is its volume correction constant B, to its specific volume V, is given by the integral of the pressure correction with respect to the specific volume V from B to V. By substituting the expression obtained for the pressure correction into the integral and performing the integration, we can write the specific work as minus the modified pressure correction constant A prime over the specific volume V, plus the constant A prime over the volume correction constant B. The first term in the right-hand side is negative, indicating that the pressure volume work done by the expanding gas reduces its internal energy. The second term is a constant determined by the properties of the gas, and it can be dropped from the right-hand side when the specific pressure volume work is subtracted from the specific internal energy of the gas. In this interpretation, the internal energy of a fond der Waals gas is the sum of the temperature-dependent internal energy derived from the ideal gas approximation describing the behavior of the real gas in zeroth order, and the correction term minus A prime over the specific volume V describing the work done against the intermolecular forces between the gas particles in the fond der Waals approximation. The fact that the internal energy of a real gas depends on its volume has the obvious consequence that the gas must cool down during its expansion. We already discussed the free expansion of an ideal gas when we presented the experiments on the expansion of air that was performed by Gay-Lussac in 1807 and Joule in 1845. The apparatus used by Joule in his experiment consists of two identical gas containers connected with a tube that has a valve, and placed into a vessel filled with water serving as a calorimeter. The valve is closed, separating the containers of volume V1, and one of them is filled with air at a given pressure P1 and temperature T1. In the experiment, the valve is opened, and the gas is free to expand so as to fill the entire volume V2 of the containers. After the final equilibrium state has been reached, the temperature T2 and the pressure P2 of the whole system are measured. The total volume V2 of the system is given by 2 times the volume V1 of the individual containers. The first law of thermodynamics tells us that the change in the internal energy of the gas due to its expansion is equal to the sum of the heat Q absorbed by the gas and the pressure volume work W done on the gas. Since no heat flowing through the walls of the containers is measured by the calorimeter, and no pressure volume work is done on the rigid walls of the containers, the difference between the internal energies U2 and U1 vanishes. That is, the specific internal energy of the gas is the same before and after its expansion. The specific internal energy of a real gas is given by the difference between its specific heat capacity CV at constant volume times its temperature T, and its modified pressure correction constant A prime over its specific volume V, and this expression can be substituted into the first law. This gives an equation stating that CV times T1 minus A prime over V1, minus CV times T2 plus A prime over V2 vanishes. If we express the difference between the temperatures T2 and T1, we can write it as A prime over CV, times the difference between 1 over V2 and 1 over V1. Here the relationship between the volumes V1 and V2 of the gas before and after its expansion shows that its specific volume V2 is greater than its specific volume V1. As a result, the right-hand side of the equation describing the difference between the temperatures of the air before and after its expansion is negative, that is, free expansion cools the gas. However, this cooling could not be detected by the apparatus used in the Gay-Lussac experiment due to its low sensitivity. In order to overcome this difficulty in the temperature measurement, Joule and Thomson later developed a much more accurate method to examine the variation in temperature during the free expansion of real gases. In their experiment conducted in 1852, Joule and Thomson studied the expansion of a gas through a porous plug in a thermally insulated tube. As the modern version of their apparatus built for demonstration purposes shows, in the experiment a constant flow of gas is maintained along a double piston cylinder that is separated into 2 compartments by a rigid porous plug. At the initial position of the piston in the left-hand side, the compartment between the piston and the plug has a volume V1, whereas the piston in the right-hand side is exactly at the plug, leaving no space between the plug and the piston. The initial temperature and pressure of the gas in the compartment are denoted by T1 and P1. As constant pressures are applied to both of the pistons, the gas in the left compartment is slowly throttled irreversibly to the right compartment. A force somewhat greater than the force F1 given by the product of the pressure P1 and the cross-sectional area A of the piston is applied to the piston, pushing the gas through the plug into the right compartment. The gas flows slowly enough through the plug so that the gas on the upstream side of the plug remains at the uniform pressure P1, and the gas on the downstream side is at a uniform pressure P2. On the downstream side, a force somewhat smaller than the force F2 given by the pressure P2 times the cross-sectional area A of the piston is applied to the piston so that the gas could only slowly expand. At the final position of the piston on the upstream side, there is no space left between the piston and the plug, whereas the compartment on the downstream side has the volume V2. On the upstream side, at a higher pressure is applied to the piston than on the downstream side, and the initial volume is less than the final volume of the expanding gas. The temperatures T1 and T2 of the gas are carefully monitored on either side of the plug. The measurements show that the temperature of the downstream gas in general is different from that of the upstream gas. Depending on the type of the gas, its initial temperature and pressure, and the pressure drop between the compartments, the temperature of the gas can either decrease or increase as it passes through the plug. This temperature change is called the Joule-Thomson effect. For example, the results of the experiment performed with air and hydrogen in the range of atmospheric pressure, where the pressure drop is 1 atmosphere, are the following. For air, the difference between the initial and the final temperatures of the gas is about 1/4 degrees Celsius, which means air cools down during the Joule-Thomson expansion. For hydrogen, this difference is equal to about -1/40 degrees Celsius, that is, hydrogen warms up during its expansion. Because the cylinder is thermally insulated, there is no heat exchange through its walls, that is, the heat Q absorbed or released by the gas is equal to 0. The pressure volume work W done on the piston while the gas is expanding can be written as the difference between the product of the initial pressure P1 and the initial volume V1 and the product of the final pressure P2 and the final volume V2. The first law of thermodynamics tells us that the change in the internal energy U of the expanding gas given by the difference between the final internal energy U2 and its initial internal energy U1 is equal to the heat Q exchanged between the gas and its surroundings plus the pressure volume work W, that is P1 times V1 minus P2 times V2. This gives the equation stating that the internal energy U1 plus the product of the pressure P1 and the volume V1 is equal to the internal energy U2 plus the product of the pressure P2 and the volume V2. Since the enthalpy of a thermodynamic system is defined by the sum of its internal energy U and the product of its pressure P and volume V, the equation tells us that the initial enthalpy H1 of the gas is equal to the enthalpy H2 in its final state. This result shows that the Joule-Thomson expansion of a real gas occurs with constant enthalpy, that is, we talk about an isenthalpic process where the change dH in the enthalpy of the gas is equal to 0. By comparing this finding with the one of the Gay-Lussac experiment where the specific internal energy of a gas during free expansion is constant in the ideal gas approximation, we can see that the specific enthalpy of a gas is constant during the Joule-Thomson expansion in the case of a real gas. It follows from the equation in the left-hand side formulating the first law of thermodynamics that two possible cases exist for such an isenthalpic process. In the first case, the product of the pressure and the specific volume of the gas in its initial state is less than the same product in its final state. This means that the pressure volume work on the piston is done by the gas while it is expanding, and its specific internal energy U must decrease to hold its specific enthalpy constant. As a result, its temperature T decreases as well, that is, the gas cools down during the Joule-Thomson expansion. The second case is the opposite, where the product of the pressure and the specific volume of the gas in its initial state is greater than the same product in its final state. That is, the pressure volume work done on the piston is negative since the piston does work on the gas during the expansion. As a result, the specific internal energy U of the gas increases and the temperature T of the gas increases as well, that is, the gas warms up during the Joule-Thomson expansion. In order to examine the opposite cases or the inversion in the cooling or heating of a real gas during its isenthalpic expansion, we will introduce the Joule-Thomson coefficient of the gas. When determining the differentials of thermodynamic potentials, we wrote the differential of the enthalpy H as the sum of the temperature T times the differential of the entropy S and the volume V times the differential of the pressure P, which vanishes in the isenthalpic process of the Joule-Thomson experiment. Because the entropy S of any thermodynamic system can be expressed as a function of the temperature T and the pressure P at given number of particles n in the system, its differential is equal to its partial derivative with respect to the temperature T at a constant pressure P times the differential of the temperature T, plus its partial derivative with respect to the pressure P at a constant temperature T times the differential of the pressure P. If we substitute this equation into the differential of the enthalpy H, we obtain T times the partial derivative of S with respect to T at constant P times dt, plus the partial derivative of S with respect to P at constant T times dP, plus V times dP. In the first term in the right-hand side of the equation we can replace the partial derivative with the heat capacity Cp of a gas at constant pressure given by its temperature T times the partial derivative of its entropy S with respect to T at a constant pressure P. We could cast the partial derivative in the second term into another form as well when we presented Maxwell relations. By using the mnemonic sentence "the friendly vagabond usually shares his precious gifts," we can reproduce the thermodynamic square which we apply to express the partial derivative of the entropy S at the top left corner of the square in terms of the partial derivative of the volume V at the adjacent corner. If we rotate our position at the corner of the entropy S counterclockwise, then we reach the pressure P at the adjacent corner, which is applied as the independent variable in the derivative of the entropy. A further rotation gives the position of the temperature T, which serves as the constant parameter of the derivative of the entropy with respect to the pressure. For the partial derivative of the volume V in the right-hand side of the relation, we rotate our position at the volume V clockwise and select the temperature T as the independent variable in the derivative of the volume. By rotating our position further, we arrive at the position of the pressure P and use it as the constant parameter of the derivative of the volume with respect to the temperature. Since minus the entropy has the sign opposite to the one of the volume, we write a negative sign in the right-hand side when we express the derivative of the entropy as minus the partial derivative of the volume V with respect to the temperature T at a constant pressure P. By inserting these expressions into the equation describing the differential of the enthalpy H, we can write it as the heat capacity Cp at constant pressure times the differential of the temperature T, minus T times the partial derivative of the volume V with respect to T at a constant pressure P times the differential of P, plus the volume V times the differential of P. Because the thermal expansion coefficient alpha of a gas is given by 1 over the volume V of the gas times the partial derivative of V with respect to the temperature T of the gas at a constant pressure P, which can also be expressed in terms of the molar volume Vm, dH is equal to Cp times dt, plus V times 1 minus T times alpha, times dP. For isenthalpic processes the left-hand side vanishes, and we can formally divide this result by the differential the pressure and write the equation stating that the heat capacity Cp at constant pressure times the partial derivative of the temperature T with respect to the pressure P at a constant enthalpy H, plus the volume V times 1 minus T times the thermal expansion coefficient alpha vanishes. If we define the Joule-Thomson coefficient mu sub Jt of a gas by the partial derivative of its temperature T with respect to its pressure P at a constant enthalpy H, then it can be written as the ratio of the volume V of the gas to its heat capacity Cp at constant pressure, times the product of its temperature T and its thermal expansion coefficient alpha minus 1. This coefficient describing the Joule-Thomson effect for real gases vanishes for an ideal gas since there is no change in the temperature of an ideal gas during its free expansion. The Joule-Thomson coefficient is a function of the temperature and volume of a real gas, and its sign determines whether it cools down or warms up during an isenthalpic expansion. We have introduced the Joule-Thomson coefficient for real gases which we described by applying either the ideal gas law or the von der Waals approximation. We have already stated this coefficient vanishes for an ideal gas since there is no change in the temperature of the gas during its free expansion. That can immediately be seen if we substitute the ideal gas law into the expression obtained for the Joule-Thomson coefficient. The ideal gas law states that the product of the pressure P and the volume V of the gas is equal to its amount of species N times the gas constant R times the temperature T of the gas. We have expressed the Joule-Thomson coefficient in terms of the thermal expansion coefficient alpha of a gas defined by 1 over the volume V of the gas times the partial derivative of V with respect to the temperature T at a constant pressure P. Then we can replace the volume of the gas in the derivative by applying the equation of state of an ideal gas and compute the derivative, which gives 1 over V, times N times R over P. By substituting the ideal gas law into the right-hand side we obtain 1 over T. As a result, the Joule-Thomson coefficient mu sub Jt given by the ratio of the volume V to the heat capacity Cp at constant pressure, times the temperature T times the heat expansion coefficient alpha minus 1, has a vanishing expression in its parentheses and the coefficient is equal to 0 for an ideal gas. For a von der Waals gas the equation of state tells us that the sum of the pressure P of the gas and its pressure correction constant A over the square of its molar volume Vm, times the difference between Vm and the volume correction constant B of the gas, is equal to the gas constant R times the temperature T of the gas. The left-hand side of the equation of state can be written as P times Vm, minus P times B, plus A over Vm, minus A times B over Vm squared. If divide this equation by the pressure P, we can express Vm as R times T over P, plus B, plus A over P times Vm, minus A times B over P times Vm squared. Instead of solving this cubic equation for the molar volume Vm, we apply the ideal gas approximation where we write the equation of state in terms of the molar volume Vm of the gas, stating that the product of the pressure P of the gas and its molar volume Vm is equal to the gas constant R times the temperature T of the gas. By using this equation, we can eliminate the molar volume Vm from the last two terms in the right-hand side of the equation obtained for the molar volume Vm. Then Vm can be approximated as R times T over P, plus B, minus A over R times T, plus A times B times P over R squared times T squared. If we insert this result into the definition of the thermal coefficient alpha of the gas expressed in terms of the molar volume Vm and compute the partial derivative of the molar volume with respect to the temperature T at a constant pressure P, then we obtain an approximation of the thermal expansion coefficient given by 1 over Vm, times the quantity of R over P plus A over R times T squared, minus 2 times A times B times P over R squared times T cubed. We substitute this approximation of the thermal expansion coefficient alpha into the expression obtained for the Joule-Thomson coefficient, where the volume V is written as the amount of species N times the molar volume Vm. Then the coefficient can be approximated by N over Cp times the quantity of T times R over P, plus A over R times T, minus 2 times A times B times P over R squared times T squared, minus Vm. Here we write the ratio of the heat capacity Cp to the amount of species N as the molar heat capacity C sub Pm, apply the ideal gas approximation for the molar volume Vm again, and simplify the result. The first and fourth terms immediately cancel out each other, whereas we can add the second and the sixth terms, and the third and the last terms together. As a result, the Joule-Thomson coefficient of a fond der Waals gas can be approximated by 1 over the molar heat capacity C sub Pm at constant pressure, times the quantity of 2 times the pressure correction constant A of the gas over the gas constant R times the temperature T of the gas, minus the volume correction constant B of the gas, minus 3 times A times B times the pressure P of the gas over R squared times T squared. This result shows that the Joule-Thomson coefficient of a gas depends both on its physical properties and its temperature and pressure. In many cases the last term of second order in the temperature is dropped from the approximation, showing that the coefficient depends on the temperature but not on the pressure in the first order. Since defined by the derivative of the temperature with respect to the pressure, the coefficient vanishes at the inversion temperature of the gas. In order to study the phenomenon of inversion, we consider the Joule-Thomson coefficient defined by the partial derivative of the temperature T of the expanding gas with respect to its pressure P at a constant enthalpy H, which was also written as the volume V of the gas over its heat capacity Cp at constant pressure, times the temperature T of the gas times its thermal expansion coefficient alpha minus 1. Because it is already approximated in terms of the fond der Waals constants A and B of the gas, we cast the coefficient into the form stating that the volume correction constant B over the molar heat capacity C sub Pm of the gas at constant pressure times the square of the temperature T of the gas, times the quantity of 2 times the pressure correction constant A over the gas constant R times B, times T, minus T squared, minus 3 times A times the pressure P of the gas over R squared. By definition, the coefficient is equal to the slope of the isenthalpics in the temperature versus pressure diagram of the gas under the Joule-Thomson expansion. Here we plotted the curves representing the temperature of the gas as a function of its pressure at constant enthalpy for nitrogen. As already mentioned, the definition of the coefficient also shows that for a negative Joule-Thomson coefficient the gas is cooling down during its isenthalpic expansion. If the Joule-Thomson coefficient is positive, then the gas is warming up or reheating during its isenthalpic expansion. This inversion indicates that the thermodynamic states where the coefficient is equal to 0, no cooling or reheating occurs during the isenthalpic expansion of the gas. For a vanishing Joule-Thomson coefficient there is a so-called inversion curve in the temperature versus pressure diagram of the expanding gas, where the inversion temperature TINV is defined by the expression stating that the inversion temperature times the thermal expansion coefficient alpha is equal to 1. This condition involves that the expression in the parentheses of the approximation must be equal to 0. And at the inversion temperature we have the equation stating that the square of the inversion temperature TINV, minus 2 times A over R times B, times TINV, plus 3 times A times P over R squared vanishes. For a given gas with the fond der Waals coefficients A and B and for a given pressure P, This equation determines the inversion temperature of the gas in the Joule-Thomson expansion. The inversion curve, that is the points representing the inversion temperatures in the temperature versus pressure diagram, is defined by the maxima of the isentalpics, as seen in the figure. The diagram also shows that two inversion temperatures exist for a given pressure below a maximal pressure, and the difference between them increases with decreasing pressure. The maximum inversion temperature can be obtained from the equation of the inversion temperature evaluated at zero pressure, which gives 2 times the pressure correction constant A over the gas constant R times the volume correction constant B. If we calculate the temperature where the derivative of the equation of the inversion temperature vanishes and substitute it into the equation, then we can solve it for the pressure. This gives the maximum pressure where the inversion effect exists, which is equal to the pressure correction constant A over 3 times the square of the volume correction constant B. At the same time, the inversion curve separates the region of cooling from the region of reheating, represented by the blue and the red areas in the diagram. We note that the regions of cooling and reheating are limited by the region of liquid phase, as the purple area shows. If the gas is in the thermodynamic state represented by any point in the blue area, then the gas does work against the molecular forces during its expansion, which reduces its internal energy and the gas cools down. The inverse scenario is where the gas is in a thermodynamic state represented by any point in the red area. Then an external pressure volume work is done on the gas, increasing its internal energy, which usually results in the reheating of the gas. The table shows the maximum inversion temperature for different substances from helium to oxygen, where we can see that this temperature is low for lighter gases like helium or hydrogen, indicating that they have much weaker intermolecular forces than a nitrogen or an oxygen gas. We also note that due to the difference in the pressure in the upstream side and the downstream side of the throttling, the Joule-Thomson expansion is irreversible. There is no thermodynamic equilibrium between the two sides at different pressures, even if the gas flow is slow, that is, the process is not quasi-static. The irreversible expansion of gases are very useful in producing very low temperatures, and it is applied in liquefaction of gases. For example, nitrogen and oxygen with their high maximum inversion temperatures are good candidates for such a procedure, since they are easier to liquefy than helium.